In lesson 6.1, we're going to be talking about the properties and the attributes of polygons. So first we want to start by defining what a polygon is. Now, a polygon is a closed plane figure formed by 3 or more line segments. Each segment intersects exactly 2 other segments only at their endpoints. And I'll remind you that that one single endpoint is called a vertex. No 2 segments with a common endpoint are collinear, so they don't overlap. If you take a look at the chart, I like to compare those shapes that are considered polygons and those that are considered not polygons. You'll notice that a circle is not a polygon because it doesn't have any line segments. And our polygon doesn't necessarily have to be a pretty normal looking shape. It can be kind of odd looking, but it has to be a plane figure that is a closed plane figure. So I cannot have a curved side. I cannot have a line segment hanging out. I can't have an open space. I can't have overlap, and it cannot be three-dimensional. When we talk about polygons, we also may be talking about their diagonals. And a diagonal is simply a line inside of my polygon, or line segment, excuse me. By definition, it says it is a segment that connects any 2 non-consecutive vertices. Non-consecutive meaning not in a row, okay? B and D are non-consecutive vertices. B and E are non-consecutive vertices. Now, if I would say B and A or A and B, those are consecutive, and if I connected those, that would be a side of my polygon. Non-consecutive vertices connected would give me a diagonal. And of course, you know from before that you name your polygon according to its number of sides that it has. So as you look below, hopefully you are familiar with some of these names for your polygon. You might have to refresh your memory a little bit. Some of them you don't see quite as often as others. For example, you may not remember that a 7-sided figure is a heptagon, or a 9-sided figure is a nonagon, or 12-sided is a dodecagon. Can you have a polygon that has more than 12 sides? Yes, you can, but there isn't a word name for that. So for example, if I had a polygon that had 15 sides, it would simply be called a 15gon. N is an n-gon. Anything above 12 sides is going to be named in this fashion. 20 sides, 20gon, and so on. So in example A, they just ask us to decide if we have a polygon. If our answer is yes, they want to know what you would name it. Question number 1, can I consider this figure a polygon? Yes, it is a closed plane figure. It would work as a polygon. If I count up the number of sides, I find there's 7 sides, and so this would be named a heptagon. Number 2, is number 2 a polygon? No, it is not. I cannot have the curved sides. Is number 3 a polygon? No, it is not. I cannot have the open space. Is number 4 a polygon? Yes, number 4 is a closed plane figure. Counting up the sides, I see there's 9 sides, and so we would name this a nonagon. Continuing on page 2, we're going to talk about a little bit more polygon vocabulary. We can think about whether we classify our polygons as equilateral or equiangular. We know from first semester that equilateral means all the sides are the same, and that equiangular means all the angles are the same. Now, that can be equilateral polygon, but not necessarily equiangular, or vice versa. But if my polygon is both equilateral and equiangular, we're going to consider that a regular polygon. Okay? To me, a regular polygon are the polygons that you see on a poster. They're kind of poster perfect polygons. In fact, that's what I think about. I think about the word perfect because they often look very nice. They're equilateral and they're equiangular. Now, if my polygon is not regular, such as this one up here, they're going to consider that to be irregular. I can also classify my polygon as either concave or convex. You probably remember talking about these terms in science. Well, a concave polygon has an indent, right? It caves in a little bit. And a convex polygon does not. Now, by formal definition, a concave polygon really means that at least one of its diagonals is outside of the figure. And a convex polygon, all my diagonals fall inside the figure. Most polygons that we will talk about or we will discuss will be convex. Those are the polygons that you would see, again, on a poster. But looking at example B, they want us to think about how we would classify the polygons as either regular or irregular, concave or convex. So I'm going to look at these three figures. Figure number 1, I can see a lot of 90-degree angles, but my side lengths are different. And so because I have different lengths in my sides, I know for sure right away that is going to be irregular. And because of this area right here, it's going to be concave. Indent a little bit or caves in. Looking at my second figure, I can see all my sides are marked congruent, all my angles are marked congruent. That's going to mean that this is a regular polygon. And all of my diagonals would fall inside. It's going to be convex. Lastly, my third figure here, I have different side lengths. That's going to make it irregular. And because of this area here, it's going to make it concave. Again, this diagonal would fall outside of my figure. Now we're going to look at or talk about the angles of our polygons. We spent a lot of time in semester 1 talking about triangles. I know that if I take all of the angles of my triangle, that they are going to add to 180 degrees. So for one triangle, all of the interior angles are going to have a sum of 180 degrees. What about a quadrilateral? Well, if I look down below, if we knew that this was a rectangle, I know that this would be 90, 90, 90, and 90. Okay, well 90 times 4 is 360. So a quadrilateral is 360 degrees. But another way to look at that is my quadrilateral could also be divided into two triangles, 180 and 180, and that would also give me 360 degrees. That is going to be true for any type of quadrilateral. Five-sided figure, well, my five-sided figure is a pentagon, and I don't know offhand the angles of a pentagon. What would they equal if I added all of them up? I'm not sure, but I do know that I could think about splitting this figure up. And if I thought about splitting it into triangles, well, from one vertex point, I can see, well, I'd have 1, 2, 3 triangles total. Well, 3 triangles, 3 times 180 would give me 540 degrees, telling me the angles of my pentagon must add to 540 degrees. What about my six-sided figure? My six-sided figure is a hexagon. And again, from one vertex point, if I think about splitting that into triangles, although I didn't draw that very well, I can see I would have 1, 2, 3, 4 different triangles. 4 times 180 degrees, well, that would give me 720. And, in fact, that pattern would continue. For my 7-sided figure, we would end up with 5 triangles, 900 degrees total. So what happens if I have n sides? How many triangles do I have? Well, as I compare in my chart above, I can see it's always 2 less than the number of sides. So if I have n sides, I would have n minus 2 triangles. If I have n minus 2 triangles, that means my total degrees would be n minus 2 times 180 degrees. That is a formula that we can use to find the sum of the interior angles. So as you flip your paper over, the polygon angle sum theorem. Okay, well, the sum of the interior angles of an n-sided convex polygon is n minus 2 times 180 degrees, where n is the number of sides that we have. So even if I had forgot how many degrees are in a pentagon, well, I can take 5 and plug it into my formula. 5 minus 2 is 3. 3 times 180 is 540 degrees. So as I look down below, when they want me to find the sum of the interior angles of my convex 15-gon, well, 15-gon means 15 sides. If I have to find the sum of those angles, I can set it up as so. 15 sides means I really have 13 triangles that I could split that into, and 13 times 180 degrees is going to equal 2,340 degrees total. So if I add all 15 of my angles, that is what it would have to equal. Number 2, they're asking me to find the measure of each interior angle of a regular nonagon. So my reading becomes important. Nonagon means 9. Well, 9 minus 2 times 180, that would give me 1,260 degrees. But 1,260 degrees is not my answer because I want each interior angle. Because this is a regular nonagon, 9 sides means 9 angles. So we would have to go ahead and take that and divide by 9. In the end, we'd find out that each angle then would have to be 140 degrees. Number 3, it tells me that the measures of the angles of a given polygon is 2,880 degrees. I'm wondering how many sides does my polygon have? So 2,880 degrees is my total. That's kind of like my answer, where had I used my formula, that's what I would get as my answer. There's a couple ways that you could look at solving this equation. I actually would take, if we find and solve for n, we would have our number of sides. And since this is going to say the quantity of n minus 2 times 180 equals 2,880, I'm going to start by dividing each side by 180. What that tells me then is that n minus 2 equals 16. Again, solving for n, add 2 to both sides, n is 18, meaning we must have 18 sides. Number 4, it tells me that the measure of an interior angle of a regular polygon is 150. Find the number of sides. Again, I'm looking for the number of sides, but I don't have a total here. I have one interior angle. So if I had set it up as I did before, this is not true because this is the total degrees and this is one angle, each angle. So what would I have to do over here? Well, n minus 2 times 180, total degrees. If I wanted each angle, I would have to take this and I would have to divide by n. Now, sometimes kids get caught or stuck as to how they would go about solving this equation. What we want to do is we want to actually get rid of our fraction. And so I would think about multiplying each side of my fraction by n. When I do that, those are going to divide out. 180 equal to 150n. Again, there's different ways you could do this. I could divide by 180, or the other thing I could do is I could distribute that through. And I do find that a lot of times kids will go ahead and distribute that. I want to get my ends on the same side of my equation. And then we'd go ahead and we would divide. Negative 360 divided by negative 30. Well, I know I'm going to have positive. 3 into 36 goes 12 times, and so we must have 12 sides. Finally, on number 5, they're asking me to find my value for x. As I look at this equation, or this diagram, sometimes kids will say, equal it to 180. But I can't equal it to 180. This is not a triangle. This shape, 5 sides, is a pentagon. And so if you look back on the chart that we completed, or if you use our formula for a pentagon, we would find out, well, this has to actually total 540 degrees. I want to go ahead, add all of my angles up, and set that equal to 540 degrees. I have to make sure I have all 5 angles in my equation. Now I'm just going to look at combining my like terms. And solving from there. Looks like x is going to come out as 37 degrees. Okay, let's turn to the back side. We're going to conclude this lesson by talking about the exterior angles of a polygon. I can see here my exterior angles are formed when I extend one side of my angle. Here I have my triangle. My triangle has 3 exterior angles. I have a quadrilateral. My quadrilateral has 4 exterior angles. My pentagon, 5 exterior angles. Well, the question posed is asking us, does a relationship exist between the number of sides of a convex polygon and the sum of its exterior angles? Well, let's look at the sum of those exterior angles. I have 120, 100, and 140. 100, 200, 300, 20 and 40 would be 60. So that sum would be 360 degrees. Go ahead and add the exterior angles of our quadrilateral. What did you find? Your numbers, add them up, you should have found you get 360 degrees. In fact, when you add your exterior angles for your pentagon over here, you will find it equals 360 degrees. What is the relationship? Well, it actually doesn't matter how many sides your polygon has, your exterior angles will always equal 360 degrees. And I have a link here on the notes that you can check that out. It's also linked on my webpage. It shows a little demo as to why that is true. If you were to bring all of these exterior angles in to one common point, this one, this one, this one, and so on, you'd actually find they form one complete rotation. One rotation is 360 degrees. So, what does that mean? Well, the sum of the exterior angles of a convex polygon is going to be 360 degrees, no matter how many sides that you have. So if I were looking at my pentagon here and I took angle 1 plus angle 2 plus angle 3 and so on, all of those added together would equal 360. Now, looking at an exterior angle and an interior angle, here my exterior angle, let's call that X, and my interior angle Y. Well, exterior angle and my interior angle are going to be supplementary. They form or fall a straight line, and so we know that if we took X plus Y, we would get 180 degrees. Our last couple questions. Example D, wondering about finding my value for X. This is showing me my exterior angle, so what do I know? Well, I know it's got to equal 360. If I were to add them up, 139 plus 2x plus 9x plus 6x, I'm going to combine my like terms. 2 and 9 is 11, plus 6 is 17. And so I would find that 139 equals 17x. We would subtract, we would divide, and we end up finding that x should come out as 13 degrees. Now, in number 2, find the measure of each exterior angle of a regular nonagon. Well, exterior angle, I want you to think 360. But here I want each angle, so I only want one. I don't want the sum of them. A nonagon means 9. Well, if it's 9-sided, it would have 9 exterior angles. So I would simply take 360 and I would divide by 9. Because this is a regular nonagon, all of my exterior angles would be congruent. Lastly, it asks or tells me that one of my exterior angles of a regular convex polygon measures 30 degrees. Find the measure of the interior angle and the number of sides. Well, if my exterior angle is 30 degrees, that would be like my x value. We said above that my exterior and interior angles have to be supplementary. So if my exterior angle is 30 degrees, my interior angle is going to have to be 150. What about my number of sides? Well, again, I'm going to use that exterior angle. I think that's the easiest way to find it. My total exterior angles have to be 360. If each one was 30 degrees, that would tell me that I would have 12 exterior angles. Well, 12 exterior angles also means that we are going to have 12 sides. 12 sides, if I asked you to name that, then you would name that as a dodecagon. Now, if you have further questions, please stop in and see me.